Okay, great. Should I go ahead and start? All right, so let me briefly overview, I guess actually sort of this week's lectures and the plan for today. So this is a continuation of last week's lectures on spectral high-dimensional expanders of metalli. If you weren't there, don't worry about it too much. I am going to review some of the definitions. So plan one for today is to review local spectral high-dimensional expanders that metalli talked about. I, of course, won't have time to go into all of the intuition, examples, et cetera, that metalli went into. It took 4.5 hours. So I do recommend, if you haven't seen them, going back and watching those lectures as well. But I'll try to give enough information that this lecture is still relatively self-contained and followable. So please stop me at any point throughout this if a definition is unclear or something of this sort. If it's unclear to you, it's probably unclear to everybody. So please stop me. So the second part of the talk that I will do is I will introduce a viewpoint sort of similar to Quiqui's notion of spectral independence that we talked about last week, of spectral high-dimensional expanders as sort of pseudo-random or pseudo-independent distributions for objects. So I'll introduce a notion of partite high-dimensional expanders and pseudo-independence. And we'll see its connection to this original definition we talked about of local spectral HDX. And then finally, I'll actually prove some sort of classic pseudorandom properties that you might want these distributions to have. In particular, I'll prove a higher order analog of the expander mixing lemma. I'll prove high-dimensional expander mixing lemma. Where we'll see a couple core tools introduced in the proof of this as well, some higher order walks called the swap walks. And finally, if we have time, I'll talk a little bit about sort of immediate application of this to concentration and how to prove like a weak Chernoff bound for these types of distributions, just using this sort of high-dimensional expander mixing. Okay, that's the plan for today. I'll just very briefly mention for the remaining lectures, the next day after this, I'm going to talk about sort of pseudo-independent properties of these distributions that sort of go beyond what we could do previously. Everything that I've written here also sort of holds for things like expander walks. The next day we'll see applications of this type of material to agreement testing. So is there to agreement testing, which is a core of PCPs, and some properties of these types of pseudorandom distributions that seem to be much stronger than any other type of pseudorandomness we know how to construct. Siki will then talk about coboundary expansion, which is a generalization of edge expansion related to testability instead of spectral parameters. And that's sort of the overall plan for the week. OK, great. So I want to get started with review. Am I OK to erase this, Salil, at this point? OK, well, it doesn't really matter. Well, I'm going to switch these boards. Okay. Okay, so I want to start back at basics, so I'll go relatively quickly. So let's first look at the graph case. So I won't say too much about intuition on expanders. We've had the whole week on it. Everybody is pretty familiar. They're sparse graphs that mimic the properties of robust connectivity properties of the complete graph. Today we'll be talking about spectral expanders. So a weighted graph G is a vertex edge set and a distribution pi2 over the edges. Has a normalized adjacency matrix. Sorry, AG VW is equal to basically the probability of moving to W given that you are at V in the underlying random walk. So this would just be the probability of the edge VW conditioned on being at V. In other words, divided by the total sum of the weights of all the edges around V. So the sum of all neighbors W prime of V in the graph of pi2 v w prime. And you should really think of this about as the probability of w sort of conditioned on being at v. OK, so we also have, Metelli talked about this, and we'll see the generalization to hypergraphs in a second, that the edge distribution pi2 induces a marginal distribution on the vertices. Right? So induces a distribution pi1 over v. And this is just given by drawing a random edge and then subsampling a random vertex from that edge. Right? So draw a random edge, uv from pi2, and then subsample a random vertex, each of these with probability half. So that gives us a distribution over pi1. This was either in the exercises or Metelli noted it, but this induces an inner product space and expectations over edges and vertices. In particular, we have, with respect to either pi I, right, this norm fg, let's say of pi1, is just the sum over vertices in v, pi1 v, f of v, g of v. And importantly, this adjacency matrix is self-adjoint with respect to this inner product. And so it has a spectral decomposition. In particular, it has eigenvalues ranging between 1 for the all ones vector, the trivial eigenvalue, greater than or equal to between 1 and minus 1. And we call a graph an expander when essentially the non-trivial eigenvalues are bounded away from 1 or small. So let me just write the definition. So definition, G is a, so we'll actually distinguish between two different notions here, which I'm not sure was talked about in detail. It's called a one-sided lambda expander. Just if lambda 2 is less than or equal to lambda, the second largest eigenvalue. And it's called a two-sided lambda expander if both lambda 2 and the absolute value of lambda n are bounded by lambda. So if the maximum of lambda 2 and lambda n is less than or equal to lambda. OK, there's our theory of expander graphs on weighted graphs. OK, we're all happy with this. Let me move to hypergraphs and the generalized notion of spectral high-dimensional expanders and local spectral expansion. OK, so we want to generalize this notion from graphs to uniform hypergraphs. So let me start. Let's say we have a hypergraph H that is a subset of D tuples. Right? So if D was 2, this would be this collection E of edges. And I'm just sort of assuming for now this vertex set is like labeled by the numbers 1 through n. I'll sort of typically think of this as 1 through n throughout the talk for simplicity. It will be useful, as Metelli talked about more, to think about not just this collection of D tuples, but its downward closure, which is what's called a pure simplicial complex. And we'll define high-dimensional expansion based on sort of all of these subtuples, subfaces. So the pure simplicial complex sorry, I should say we'll take, just as we considered weighted graphs, we'll consider weighted hypergraphs. Yeah.
Is your indexing off by 1?
Yeah, I'm about, right. Yeah, I'm about to say, so let me just write it and I will say, I am using a different notation, unfortunately, which I apologize for. I'm about to write xi for I sets rather than I plus 1 sets, which is the math or topological notation. When we start working with partite distributions, like Kwee was talking about, things like Chernoff and high-dimensional expander mixing, notationally it's extremely annoying to use I plus 1, even though it's maybe mathematically the correct notation. So yes, thank you. This will be off by 1 from Metelli's talks. Sorry about this. So the pure simplicial complex associated with H From now on, we'll basically just write x, and we'll forget this original hypergraph. H, there's also a distribution pi d over these d sets. Just corresponds to its downward closure. So it's the union, the disjoint union of H and all of its subsets. So here xi would be all I sets that appear in some D tuple. So let me draw a picture of this. So here I'm going to be thinking about each of these as sort of a tuple in my space, like a D set through VD. This is the same picture that Mitali drew, the inclusion diagram. Down here I'll have the vertices. X1, which we were thinking of as n. And then between here I'll have the I sets. And I think it's easiest to think of this distributionally. We have a distribution over pi d, and pi d will induce, just as pi 2 induced a distribution over pi 1, the vertices here, pi d will induce distributions on all of these families of subsets. Okay, this will be, pi I through pi 1 through the analogous procedure. Right here we drew a random edge and subsampled a vertex. So I'll draw a random I set from here. Maybe let me do it here. So pi I is defined in a similar two-step process. We'll draw a D tuple randomly from pi d. And we'll just subsample a random I set from this. Let's call this S. So we'll subset a random T of size I. So this induces a distribution on all of these layers. OK. So one thing to immediately notice is that if we look at the induced distribution on edges and vertices, this corresponds to what Mitali was calling the one skeleton, or the base graph of this simplicial complex. It's sort of, yeah.
When you subsample, it's a uniform.
Yeah, thank you. Right, Mitali.
You're deleting a few vertices uniformly.
Yeah, so one way to think about generating this is we start at D, and we sort of walk down one step at a time by removing a uniformly random vertex at each step. And you can check that generating pi I sort of recursively by dropping one guy randomly each time is the same thing as drawing a uniformly random I tuple from this D tuple. Right? It's not hard to check. These are the same thing. Yeah, good. OK, so this is sort of the combinatorial base graph of this hypergraph. It captures pairwise correlations. Right? If you think about what pi 2 means, the weight of an edge is basically just counting the number of times v and w appear together in the top. So this sort of captures pairwise correlation. A natural thing to ask would be that this base graph is an expander, right? If we're trying to define a notion of high-dimensional expansion. And as Mitali talked about, this alone will be a little bit too weak of a definition. We're also going to require that sort of local neighborhoods, or what we sort of talked about as conditionings or pinnings, also have their pairwise correlations bounded, have a base graph expanding. So let me also define the links. So the link of a face tau, let's say in xi, is basically just the local component of the hypergraph that contains tau. Let me be a little bit more careful about this. So the link x tau, I guess I should give it a weight pi tau, is a d minus tau dimensional complex, where we take a look at all of the faces S that contain tau. So x tau combinatorially will be S without tau, such that tau is in S is in X. Okay, this is maybe slightly annoying to parse, but really just look at this diagram. I'm just looking at all the set of S that contain this I face tau, and then to make it a simplicial complex, I'm removing tau from that set. So this is like the higher order generalization of a neighborhood in a graph, which Metalli talked about in a little bit more depth. Okay, what do we do distributionally? We want to distribution pi tau. You should think of sort of the induced distribution on this link as just the conditional distribution of x conditioned on containing tau. Right? So a little bit more formally, we'll just look at sort of pi d on this restricted area, right? And the weight of a face S without tau in here is, again, just given by this normalized weight. So it's just pi d of S conditioned on being inside this set that contains tau. Right? So this is divided by the sum of all S prime that contain tau of pi ds prime. Okay, I'll pause briefly. Sorry for giving less intuition. Again, Metalli covered these in much more detail and more slowly, so yeah, I recommend going back to those talks for more intuition. We'll also see another version of it in just a minute. Okay, so I can now actually define a lambda local spectral high-dimensional expander, which just says that not only does this base graph expand, but in fact the base graphs of all of the links of the complex expand. So let me. Is it too low to write here? Is this OK? OK. So definition. And I guess this sort of dates back to work of Kaufman, Kazhdan, and Lubatsky. And maybe was more strictly formalized by Oppenheim. So we say that X is a lambda, all right, LSE, local spectral expander. If for all subfaces of size less than or equal to d minus 2, right? If we look at links of only one dimension, these are not graphs. These are just a bunch of isolated vertices. If I look at any link below, it's a non-trivial simplicial complex. So the link, the base graph of the link x tau is again, we have a one or two-sided notion of this definition. So it's a 1/2-sided lambda expander. Okay, I haven't really given you any intuition at the moment on why this is a reasonable definition. So I just want to pause and at least ask, is notationally or mathematically, is this definition clear? To people, it's exactly the same definition that we saw last week. Okay, so last week we did see sort of some intuition for why this is a nice definition, a little bit operationally in terms of the theorems we were able to prove using this notion. We saw this idea of sort of the local to global method, that by using all this nice local structure, we were able to take, we were able to do things like break down the Rayleigh quotient, the second eigenvalue of a global random walk, into local random walks, at which point we could use these conditional spectral gaps in order to bound its global behavior. Right? So since x tau are sort of these conditional distributions, this really gives rise to this nice notion related to like stochastic localization and things we talked about, of taking a global object you want to analyze, breaking it into local expectations, and applying this sort of nice local structure. This was sort of the core of local spectral high-dimensional expansion. And we also saw it's a good definition in part because such objects actually exist. Right? We talked about many natural dense objects, spin systems we care about that are high-dimensional expanders. And Metalli gave this nice lecture on the Kaufman-Oppenheim construction and talked about how it's actually possible to build bounded degree complexes where every vertex, families where every vertex sits in only a constant number of hyperedges that have this property. In particular, maybe I'll just write, just so people have have the context in mind. There's a theorem that I think is independently due to Lee and Lubatsky, Samuels, and Vishne that Mitali mentioned, which is there exist explicit family of lambda HDX for all lambda and dimensions D in N, where every vertex sits in, at most, something like lambda to the minus D choose 2 hyperedges. So particularly, this is an infinite family where the number of vertices n grows, but the number of hyperedges each vertex stays and remains bounded, right, which is the type of object we like to use in codes, complexity, pseudorandomness, et cetera. OK. So that's going to complete the review section from last week. Today, I want to give you sort of a different viewpoint and intuition on local spectral expanders that comes from, as I said in the beginning, viewing them as really a type of pseudorandom or pseudo-independent distribution. We saw this to some extent in Quiqui's talks on spectral independence, and I'll try to draw a few parallels to that. But yeah, so let's now talk about partite complexes and sort of rederive the notion of local spectral expansion as a view of pseudo-independence. OK, I'm going to erase this. OK, so let's talk about the partite case, which is implicitly what Quiqui was talking about in his setting. So a simplicial complex. I'll always be talking really about pure simplicial complexes in the setup I had before. I'm sort of not going to mention this again, but sorry, maybe let me say a D-dimensional or size D sets, simplicial complex, X by D is called partite, or I'll write maybe D-partite. If it's possible to partition the vertices into D sets, such that every hyperedge has one vertex from each of these D sets, right? So if it's, let's go back to this diagram. I'm trying to copy here the diagram that Mitali made in terms of the flags complex, which we saw actually an example of partite complexes. So we'll be able to partition the vertices here into D sets. And each guy here in the inclusion diagram has one vertex from each of these parts. So x0 can be partitioned into v1 disjointly. vd such that each s in xd has one vertex per part. OK, another way to think about partite complexes is the way that Quiqui viewed things, as sort of d-dimensional distributions or subsets of tuples. Right? Because there is an ordering on these parts of v1 through vd, I can view xd as a subset of v1 cross v2 cross vd, just as a family of tuples. So let me draw a diagram that looks more like this. OK, so we have sort of the simplicial view over here. Right, another way to view this is I can sort of draw my vertices out like this. Here's v1, here's v2, here's v3, et cetera, to vd. And my hyperedges are like you would have in a bipartite graph. Stretching across these D parts. OK, maybe just probably don't need to hit this point too much, but let's say we look at like an example of a tuple system n to the d. Right? What does this mean? Each of these guys is a copy of n. Over here in the simplicial complex world, again, I should think of each of these as being a copy of n, but I'm going to put like a a label on them. Sorry, this should be 1. Like this is the first coordinate copy of n. This is the second coordinate copy of n, etc. Right, so this is the simplicial complex view. This is sort of the tuple view. And because we have a distribution over this set of tuples, we can really think of this as sort of a d-dimensional distribution, right, where I guess Quiqui was drawing this as like the distribution mu over the cube or something like this. But where we generate a random element of this distribution just by picking a random tuple from our from pi d.
Do you have time to remind us an example, like the flags complex?
Yeah, I can do the flags complex. I can erase this. Yeah, so Matali actually gave this example. Yeah, I decided to skip it, but we can do it for clarity. So another version. Actually, I guess I could have just done that diagram. So maybe let me redraw. So a version that Matali talked about, it's sort of very simple but not bounded degree construction, was where our vertices were subspaces. That's sort of small, sorry. Subspaces of, I think I want fq to the d plus 1. And there is a natural ordering on these. Sorry, I should say xd. What are these? These are flags of subspaces, right? So an element in xd is like a linear subspace. It's contained in a plane, in a 3-dimensional subspace, right, all the way up to a d-dimensional subspace. So the simplicial complex view that Matali drew, here were the 1-dimensional subspaces, here are the 2-dimensional subspaces, etc. Right, and each of these flags, just like this diagram we'd had, has one subspace of each dimension. And over here in this view, this would just be, these are lines, these are planes.
See what you write.
Sorry.
Can you get a fresher marker maybe?
Yeah. I'll try to draw it bigger, sorry. That's better. So these will be, we can draw it out sort of vertically in this way. These are lines, these are planes, 3-dimensional subspaces, etc. And we have these chains, V1 is included in V2, is included in V3, etc. Right? So here are our two different views, the simplicial view and sort of this tuple or distributional view on these objects. Note that here these the sets are not actually the same size. We're not going to worry about that too much in this talk. Typically in constructions, on the vertex level, these will be the same size.
You mean that the sets of vertices?
Yeah, I mean that right, there are many more planes than lines, etc. I don't really want to worry about this for this talk. It's typically not really a problem.
In fact, one of the reasons you need these IDs is because of this.
Yeah, right. So typically, if I restrict to only looking at one part, the distribution will be uniform over that part. There's some sort of partite regularity that most of the constructions have. But of course, if this part is larger, the weight of a particular vertex here will be different, will be smaller than the weight of a vertex in other parts. So you need this, yeah.
I was just going to say that it's maybe worth saying that coset complexes also have this, are just the Kaufman-Oppenheim complex.
Right. So the other example that Matali covered, these coset complexes, right? This was like there was some parent group G and then subgroups H1 through HD, and your vertices were cosets of this. Well, this is of course the same thing. Like here's the cosets of H1, cosets of H2, cosets of H3, and by definition, each guy had a coset from one of the different colors. So basically, all of our constructions with an asterisk follow this form. Also, something that I had meant to write, which I don't remember if I did, is this bound lambda to the d choose 2 I gave, sort of the good constructions of high-dimensional expanders we have, are all one-sided partite expanders. We actually don't have very good constructions of strong two-sided expanders.
Max?
Yeah.
So I'm not really understanding the difference between the adjacent bipartite setup and just the inclusion adjacency structure, if you were to rotate it by 90 degrees and sort it by the levels, is that the same? Or?
No, it's not the same. So remember that over here, this level corresponds to like flags of I subspace, not I-dimensional subspaces, but literally like I different subspaces. Right? It's not rank I subspaces. So this is not like the Grossman poset, which is what would correspond to flipping this diagram this way. Right? These are each vertices. They correspond to these boxes on level 1. Okay, I was going to say this in a bit. A face tau here is really a partial assignment, right? This is I vertices, and over here it's going to correspond to like fixing some, I different vertices in this picture, and the link would correspond to looking at sort of the restriction to fixing this guy to be V1 and this guy to be V3, V4, etc. Yeah.
Like in particular, when we take downward closure, we've got to take all subsets. We can't like restrict one to the linear subspaces or something if we.
Right. Yeah. So if there is a whole theory of non-simplicial high-dimensional expanders, yeah, in that world you can look at sort of subsets of like the Grossman poset, which would be sort of flipping this. There's a lot of interesting research here and things to talk about, but we're going to be focusing on the simplicial complex case, which is, yeah, you have all possible subsets when you look down.
The confusion can be that there's a notion of dimension of a linear subspace. But that's not the notion we're looking at here.
Yeah.
Vertices, which are all dimension 1, can be of various linear dimensions.
Right. Yeah. You have all possible dimension subspaces as vertices, as level 1 elements. These are just pairs of vertices that are actually included as subspaces, etc. Okay. I am going to give sort of a more close connection of this view and local spectral expansion in just a second. So maybe let's move on so we can at least get through expander mixing toward the end. Okay, so taking sort of this viewpoint of d-dimensional distributions, I want to sort of talk about how local spectral expansion arises naturally as a notion of pseudo-independence. So for the moment, let's sort of forget local spectral expansion, and we'll come back to the definition in just a minute. And I basically just want to ask, if we were coming from this tuple viewpoint, right, we just have some d-dimensional distribution, when should I call it a high-dimensional expander? When is it natural to call this hypergraph expanding? There are, of course, many different notions that were studied in the literature. I'm going to start by looking at the graph case, right? So bipartite graph expansion. And I want to harken back to something that Dean talked about in one of his talks, which is expansion as a notion of sort of pseudorandomness or pseudo-independence of two variables. Right? We have a bipartite graph. So now we just have two components, right? V1 and V2. It's a weighted graph, so we have some sort of two-dimensional distribution corresponding to picking a random edge in the graph. And an equivalent way to define we can define expansion by looking at the second eigenvalue of the adjacency matrix here. But we can also equivalently define it as the fact that the variables x1 and x2 are in some sense pseudorandom or pseudo-independent. One way to think about this is that the variables x1 and x2, this two-dimensional distribution we get out, roughly speaking, is independent if and only if this graph is complete. Right? Expanders are a sparsification of the complete object, so they are sparse graphs that are highly correlated, right? You can imagine if this is only like degree 4, if I fix the value of this to be here, this is very far from independent, right? There are very few options for x2. Nevertheless, we want it to act like an independent object in some particular manner. In particular, we have a version, I guess, of what's typically called the expander mixing lemma, which just says that for all functions, let's say a function f on the left side and a function g on the right side, so f is v1 to r and g v2 to r, that the expectation of f times g across a random edge, right? So if I look at f times g across a random edge here, it should approximate expectation of f times expectation of g. right? This should be less than or equal to lambda times the 2 norm of f times the 2 norm of g, right? Dean talked about this in his talk. This is the natural notion of independence, right? We're saying that expectations of these variables split. That's a very useful notion as well. Okay, so with this in mind, we can think of expander graphs as sort of pseudo-random or pseudo-independent two-dimensional distributions. So now it's natural to ask, when should we call a d-dimensional distribution, right, in this tuple view? When should we call, x, let's think of it as a subset of n to the d, or this d-dimensional distribution, x1 through xd, in this picture over here, a lambda spectral high-dimensional expander? There are a couple of ways that you could go about doing this. Here's one that I think is particularly natural. We'll see that this is the analog of looking at the base graph in the simplicial case in a second. One thing I can do is look at all the pairwise marginal distributions of this d-dimensional distribution. Right, so I can look at the pairwise marginals xi, xj.
Consistent. Is this VI?
Yeah, okay. This is like the distribution. This is technically the support of the distribution. Is that?
So x is a
It's a set of vertices
random variable.
This is a random variable.
supported on VI.
Yes, this is yeah, okay, sorry. This is like its supports. This is the random variable. If I look at each of the marginals xi, the support of xi is the vertex set vi. Right, just to make sure everybody's fully clear on this, what does it mean to look at the marginal xi, xj? It just means I draw a full tuple, and then I drop everything that's not in coordinate ij. Right, this gives me a two-dimensional distribution, or equivalently a bipartite graph over vi cross vj in this case.
Max, if you don't mind, so just in this sort of plain bipartite setting,
Yeah.
at the top of the board, what is the law on x1, x2? Are you sampling an edge, and then
Yeah.
endpoints are x1, x2?
Yeah.
this
So the law on x1, yeah, exactly. The law on x1 is I'll sample a random edge, and then I'll project to the first coordinate.
Can you extend? Is there an analogous?
Yeah, it's the same thing, right? I take the law of pi d, like I'm generating this distribution by drawing a random d tuple, and then just projecting onto coordinates I and j, right? Like in the picture over here, I'm drawing like a random chain of subspaces, and then I'm taking only the subspaces dimension 2 and 1 of the two parts. That would be x1, x2.
So it's like a path. You've got all of these clusters. It's like a departite graph, and you're sort of
Yes.
some ordering on it, and you're doing like a path.
Yes. Yeah, I mean, not all, if you think about it as a graph, not all paths will be faces in the complex. So you have to be a little bit careful.
Yeah. but
In this case, they actually will be, but
structure.
It's a hypergraph.
yeah.
There's D hyperedges. You're choosing one hyperedge, and then you're removing everything except I and D.
I have till 30, is that right?
Yes.
All right.
But no, this plot is a couple of.
Oh, thank God. 1 or 2 minutes. Amazing. No, it's fine. We'll get through high-dimensional expander mixing. Yeah.
When you draw those D2, is it always uniformly draw, or it can have some different weights?
When we're picking the top level,
Yeah, when you sample this X1, like for the
yeah, it could have an arbitrary distribution.
weights.
Yeah, it could be arbitrary. We don't need to make any assumption on it.
But in your example, those just uniform over.
Yeah, typically, in fact, in all constructions that I know of, we typically take the top distribution to be uniform. And in application, like you usually, you're using these objects to construct something. Typically, you want the sort of final object to be some uniform combinatorial object or something like that. So we typically want the distributions to be uniform. But technically, the theory doesn't have any requirement.
General definition, it's workable.
Yeah, so right. In the general definition, it's just an arbitrary distribution. And in fact, there are cases where we care about it being non-uniform. We might look at the skeleton, like the lower dimensions of a higher dimensional object that starts uniform. This won't be quite uniform or something like this. So it does come up. And we need to work with this sort of non-uniform distribution. Yeah.
I was just gonna say that if you have to be a bit careful because like if you look at the distribution on edges, for example,
Right.
you it sort of like it might be uniform when you restrict to any pair of colors, but that doesn't mean that the mixture of like a bunch of uniform things is also uniform because they can have different support sizes. So like it's like.
Right. Yeah, I mean, okay, I'm not sure I totally understood, but it's true that when these are sort of different sizes or within lengths, when you draw a random edge, like each vertex marginally will be uniform over its part, but the edges will not. I guess in most cases the edges often are uniform between two parts.
No, that's right. In the example of the flags, the edges are not uniform. Only conditioned and
Oh, yeah.
Yeah.
Right, when you don't condition, right, sorry. Conditioned on any parts, like if I look only at 2 and 5, the distribution will be uniform, but it will be like the vertex set was weighted weirdly because they're different sizes. The different xi, xj weights globally are not going to be the same because the sizes are different. Thank you. Thanks. Okay, let me finish this definition. Right, so, okay, we said a natural condition that I sort of want to think back of hearkening to some sort of weaker notion of, Dean talked about this notion of like pairwise independence. This is some sort of spectral or proximate pairwise independence of this distribution. So maybe like approximate pairwise, I'll write /spectral independence. And this is a reasonable notion on its own, but it turns out it's not strong enough for lots of applications. What's the reason? Well, it's missing a very important property of products or independent variables, which is tautologically in an independent space. If I look at, say, I and j, and I condition on some, and I fix some value of x1, the rest of the remaining distribution, the remaining variables should not be affected. Particularly, they should remain independent. And we've seen in the last week lots of different analyses and pseudorandomness and analysis use these notions of restriction, right, where we pin certain variables and then we rely on the restriction having nice product structure. So we'll try to capture this intuition as well, and we'll require that these bipartite graphs xi, xj remain an expander. Sorry, I didn't write. These are supposed to be a lambda expander. Importantly, that's condition 1. We'll want this to remain true even after we condition on the value of any subset of the rest of the variables. Right? So this remains true even if we condition on some xs, some pinning of the values of variables in some subset S, where S is any subset of the variables outside of I and j. This is just exactly sort of this notion of pinning that was talked about in Quiqui's talks. And it also essentially corresponds in the simplicial view to taking the link, I guess technically of these would be labeled, so it would be like ZS, S. But let's not worry too much about this. Is the definition over here clear? Yeah.
Direct translation to spectral independence?
It's not quite equivalent, and let me now talk about. So local spectral expansion is exactly equivalent to spectral independence. This is slightly different because in local spectral expansion, when we look at the link of some subface ZS, we're looking at the base graph of all the rest of the variables. Here, we're only looking at the sort of the bipartite components. So I want to actually draw an example to make this clear.
What do we call these? Like,
oh, thank you. Sorry. Yeah. This is typically called a lambda product. I guess there may be different names in the literature. It appeared explicitly in work of Gerlifshitz. The pen is try to press harder.
There's another one.
There's more ones near you.
Like this. Probably I just need to write harder. 22. It also sort of implicitly appeared in some earlier works of Yotam and Aritz, Justin Denner, 19, and also in a joint work with Bafna, Kaufman-Levitt. Anyway, we'll see that it's basically equivalent to the notion of local spectral expansion quantitatively up to some very small changes. Okay, let me. So I do now want to talk about the connection of local spectral expansion to this. Maybe I'll be a little bit brief so we can get to high-dimensional expander mixing.
We'll try not to live.
Sorry? No, it's good. I mean, we can always just cover the remaining things in the next, did I drop something? In the next lecture. Okay, so I want to sort of make three connections of this notion of lambda products. So maybe I'll pull this over to our original definition of local spectral expansion. Okay, the first thing that I want to say is that our definition of local spectral expansion, I claim sort of is actually the natural analog of this definition for the unordered case. Right? We can view when we have this, xd as just being a subset of d tuples and not necessarily ordered in some way, then we sort of correspondingly have this unordered d-dimensional distribution of sets. And what's sort of the analog of this definition? Well, we wanted all pairwise marginals to expand, then we wanted this to hold under conditioning. What's the natural sort of pairwise marginal of an unordered set? Well, I should just draw a random d-tuple and subsample an edge from it randomly. Right? This gives me sort of the natural marginal distribution over edges. Right? So draw S from x1, xd, subsample an edge VW uniformly at random from S. But this is exactly how we defined pi2, right? The edge distribution on our simplicial complex. Over here, in particular, this is just the base graph, right? This two-dimensional marginal, it's just exactly the base graph in the simplicial complex view. So this first condition is the analog of saying the base graph expands. And again, I'm not going to go through it in too much detail, but the fact that this holds under conditionings, right, this is exactly saying that, conditioned on drawing a set that contains some fixed tau in xi, right? So we're drawing this d-face condition on containing tau. This is exactly saying this two-wise marginal approximate independence should hold under conditioning. So links being expanding are exactly this conditional condition. So in some sense, local spectral expansion is the natural generalization of this notion of lambda products. Okay, it's also quantitatively very deeply connected to it. So let me now say sort of the second connection. If X is actually a partite complex, it turns out these notions are essentially equivalent. And so if X is a d-partite complex, then the following hold. One, if X is a lambda product, it's automatically a lambda local spectral expander. By the way, these will be exercises. So maybe I'll just briefly give intuition. This is coming from what we were talking about before, that in this view over here, the one skeleton is basically just the multipartite graph that has all of these bipartite xi, xj components. So a lambda product is requiring that every bipartite component expands. Local spectral expansion says, look at the entire multipartite graph. That full thing should be an expander. So these are essentially equivalent. So the bipartite expansion turns out to be stronger. Having every part expand is stronger than the entire thing expanding. That's a simple exercise. Slightly less simple, it turns out that any lambda local spectral expander is a lambda over 1 minus d minus 2 lambda product. This is a little bit less obvious. If you look at this and you remember last week's lecture, you maybe have some idea that this comes from some form of trickling down theorem. And this is true. I should also say this result was sort of already known before the notion was introduced. It's in this paper of Dickstein and Deneur. It's like a partite version of the trickle down lemma, also an exercise. Okay, I'm actually fine on time. Okay, I want to say one more connection between them, and then we'll actually prove some like global pseudorandom property of these objects. The third thing I want to talk about is to say that up to, I guess, thinking about one-sided non-partite complexes, you can pretty much just always worry about this notion. In particular, I claim that this is sort of more general than two-sided unordered local spectral expansion. So what do I mean? So there's a classic connection in the graph case between two-sided expansion and bipartite expansion. Right? If I take a graph, a non-bipartite graph G that is a two-sided lambda expander, if I take its bipartite cover, right, what does this mean? I take two copies of its vertices, right, like v cross 0, or maybe v cross 1, v cross 2. Sorry, it's sort of abysmal handwriting down here. And we'll draw an edge in this graph between v0 and w1 when vw is an edge in the original graph. It's quite easy to show that this graph is a bipartite lambda expander. Right, so this is a lambda expander. It's, again, a fairly easy exercise to show that this holds also in the dipartite setting. Right, so I can define, let me sort of reuse this picture over here. Well, I'll erase it and redraw it. Oh, you can't see here. Well, can I erase this? So, okay, I mean, you probably all know what I'm going to say already, but just to be sure, there's of course a natural, dipartite analog of this cover operation, right? If I just have an unordered simplicial complex that's a lambda two-sided local spectral expander, the dipartite cover again takes d copies of the vertex set. So x1 cross 1, x1 cross 2, etc. And again, exactly the same definition. v0, sorry, v1, v1, 1, v2, 2 to vd. D is a hyperedge in this cover exactly when v1, v2 through vd forms a hyperedge in X, right? If the set v1, vd lies in xd. Right? So it's exactly the natural notion of a cover. Another way to think about this is I include sort of all possible orderings of every set. So it's quite easy to show, and again, a good exercise in understanding sort of the various distributions, that if this is a lambda two-sided LSD, this partite embedding is a lambda product. So typically, we can just focus on proving things for lambda products, and we'll automatically get the same result on two-sided lambda high-dimensional expanders. OK, maybe you'll ask me, what about one-sided non-partite high-dimensional expanders? There are very important objects that satisfy this, like the Queequeg we talked about, expanding trees, matroid bases, things like this. In the actual construction of sparse high-dimensional expanders and using them as a gadget, our constructions are already all typically partite, and since the point here is we get to we get to construct our gadget, I sort of don't have to worry so much about the one-sided case, since it's not the case that we have much better constructions of, say, one-sided non-partite objects. Yeah, Salil.
So I missed the direction that you're using this correspondence. Like, 'cause earlier you were saying that we have better one-sided constructions than
Right.
two-sided ones. So is this giving some way to get a two-sided thing out of the one-sided constructions or not?
No, this is saying, like, take any two-sided guy, I can embed it as a partite one-sided thing. So if I've already proved some nice theorem for partite one-sided high-dimensional expanders, then the theorem will hold on two-sided. Some version, natural version of the theorem will hold for the two-sided case. So I'm just saying I can focus on proving things for this lambda product model and not worry about having to prove it for unordered two-sided HDX. The one-sided versus two-sided, I don't want to go deeply into it because I don't have that much time. The only way we know how to construct two-sided high-dimensional expanders is by taking a one-sided high-dimensional expander and then considering a lower dimensional skeleton. And a version of the trickling down theorem actually tells you that the negative eigenvalues get better as you walk down the complex. but this results in horrible parameters. So typically you actually want to work with one-sided partite objects because their parameters are much, much better than what we know how to build in the two-sided case. Although I don't know if that's inherent. We might just not have constructions.
Thanks.
Okay, yeah. Yeah, Noah.
I just wanted to check, so the difference between local spectral expansion and productness, like in 2, is that local spectral expansion is about the whole multipartite graph that you get when you condition on.
Right, yeah, thank you. I wanted to actually draw this example for 3 dimensions to sort of see the difference. Right, in the 3-partite case, we have like, x1, x2, x3. In this case, the conditionings are actually the same. Right? If I like fix x1 to be some particular value, I just get a graph here, and this local graph conditioned on v is exactly the link of v in this object. So in this place, they're actually the same. When I look at the base graph, local spectral expansion is saying, take a look at sort of the 3-partite graph, where each component between I and j is exactly the graph xi, xj, and we want this 3-partite object to be an expander. A lambda product just says, I'm going to require that every bipartite component xi, xj is an expander. They're very closely related notions. Yeah, okay, so yes is the answer to your question. I just reminded me I wanted to give this basic example. Okay, so in the last 20-ish minutes, I now want to prove that this notion actually implies sort of standard or natural global pseudorandomness of these distributions. In particular, I want to prove a variant, I erased it, of the expander mixing lemma, or this alternate characterization, right? Expectation of f times g is close to expectation of f times expectation of g. Ah, it's right there. Thank you. In fact, I'm sort of surprised that somebody didn't ask me if we're generalizing this. Why don't we just take this to be the definition, right? You could have functions f1 through fd on each of the parts. Why don't we just define it to be expectation of f1 through fd splits as the product of expectations? And what I'll roughly show you is that, in fact, this is basically equivalent. If you require this in all links of the object, this is basically just the same definition. So mostly the difficulty is one way. One direction is just the trickle-down theorem. If all the codimension 2 links satisfy this, it's literally equivalent. Right? Bipartite expansion is equivalent to this notion. What I'm going to show you is the other direction, that lambda products satisfy a high-dimensional expander mixing lemma. OK, so let's go ahead and do this. Maybe I shouldn't have erased this definition. Oh well. OK, so what we want is the natural analog of this theorem for lambda products. So this sort of high-dimensional expander mixing lemma, it's been studied a number of times throughout the literature. High-dimensional EML. Probably people in the audience maybe actually have a better idea than me. I know that Izar had some version of a proof of this in one of his earlier papers of some sort of type of high-dimensional expander mixing. Another version was in this paper of Yotam and Aritz. The version that I'm going to be telling you is from a joint paper with Yotam. Yeah, so there's an early. I think there's an earlier paper that I'm. Yeah, okay. I apologize to. Yeah. Thank you. I think that those might have been specific to the Ramanujan complexes. These are for general local spectral expanders or lambda products. I'm basically going to be following the argument in this paper, and I'm actually going to give a slightly improved version that's a little bit more natural that was for this talk. OK, so what's the statement? Let's say that x is a d-partite lambda product. The theorem is the following. It's just like pretty much exactly what you think it's going to be. It says for all bounded functions, not bounded, for all functions, I guess I'll write vi, which remember is the support of xi. Sometimes I write xi by mistake, but if we have a collection of functions, one on each part, right, f1 through fd, we want that the expectation of the product of f1 times FD is close to the product of the expectations up to some sort of corresponding spectral error. This will be is less than or equal to. I'm not going to prove like an exactly tight version in this coefficient, but we'll prove d over 2 times log of d times the product to d of the d norms of these functions. Right, so if we specify d to be 2, which was the graph case, this is log base 2, so this becomes 1, and this becomes the product of the 2 norms. So this exactly specializes to the expander mixing lemma. And in the general d case, we get, I'm sorry, there should be a lambda there. Yeah, d over 2 log d, which is some high dimensional version coming from the d partateness, times lambda times the product of the d norms. Okay, I'm just going to prove the upper bound, that this is without the absolute value. Yeah?
So the expectation on the right-hand side is with respect to which distribution?
Over the FIs. This is with respect to the marginal distributions over each xi, right? So just draw a d-tuple, project to coordinate I. Yeah, it's like the natural one that you would expect. Again, typically in most constructions, this ends up being uniform. At least in many bounded degree constructions, it's just uniform over the part. Okay, questions about the statement? The only difference is that we've basically traded 1 with some coefficient of d, and the 2 norms have been generalized to the d norms of the function. Okay, great. So let's make an attempt at proving this. So I want to very briefly start with the proof of the 2-dimensional case, or really just a few lines, and then we'll see how it generalizes to this d-dimensional setting. So the standard expander mixing lemma, right, which I've written over here, we have just this 2-dimensional case x1, x2. We have that we want to prove the expectation of f. Let's say we draw an edge v1, v2 from x1, x2, that f v1. So we have functions f and g. We want to upper bound this by product of the expectations times some lambda error. What are we going to do? Well, the first thing I'm going to do is say, instead of drawing a random edge, I'm going to draw first v1 and then v2 conditioned on v1, right? v2 from the link of v1, or conditional distribution. So this is equal to expectation of v1 drawn from the marginal on x1 of f of v1 times now the expectation of v2 drawn from x2 conditioned on v1, sorry, conditioned on x1 equals v1, or equivalently from the link of v1 of g of v2. And then I want to notice that this is just an application of the bipartite adjacency matrix, right? So we defined this adjacency matrix before. It's exactly the same definition, so maybe I won't. Did I have, do I have it somewhere?
I thought you were going to draw the bipartite.
Oh, I can draw the, sure. I mean, the adjacency matrix over here is just like this v1 by v2 matrix, where again, the value here is just the probability of moving to v2 given, sorry, the value ag v1 v2 is just the probability of moving to v2 given that you're at v1. So the conditional probability of v2 and the link of v1. Just the standard bipartite graph definition, nothing fancy. Right, so this is equal to expectation over v1 x1 of f of v1 as the adjacency matrix f2 of v1, just by definition. And now we'll apply the second eigenvalue bound on ag. Technically, I'm skipping the step where I decompose this into its parallel and perpendicular components. It's a very standard spectral graph theory. That's what's going on here. But I can bound this by sort of the parallel component, which is the expectation of f times the expectation of g. And then the remaining components are dampened by the eigenvalue lambda. Right, so plus lambda times the 2 norm of f times the 2 norm of G. Okay, so all we're doing is using the fact that this is really f of v1 times adjacency matrix of, sorry, this should be G. I was using that instead. No, of v1. Right, this averages over all the neighbors of v1, which is exactly v2 conditioned on v1. Good. Okay, we're happy with that? So let me now try to do the d-partite version. So we're basically going to try to follow the same strategy. Here, what we sort of did was we split the function in two, and then we applied expansion of this, right, the f part and the g part. I applied expansion of the operator, and I split the expectations. I'm going to try to do exactly the same thing in some sort of higher order analog of this. Okay, so now we have the expectation of f1 times f2 times f3 fd over v1 vd drawn from x1 xd. So I'm going to assume that d is a power of 2 to make things simple. There is a way to do this when d is not a power of 2, but it's a little more complicated. So what I'm going to do is split this in half. Right, I'm going to consider the function fl, which is just going to be the product of f1 through fd over 2. And fr, which is the product from d over 2 plus 1 to d of fi. I'm also going to write some notation. I'm going to define mu of L to be the product of the expectations of this. So this is going to be the product from I equals 1 to d over 2 of the expectation of fi. Mu r is going to be analogous. It's the product of the expectations over the other half. And now I'm going to do sort of exactly what I did before here, but replacing f and g with fl and fr. Right, so I'm going to write this expectation, f1 v1, f2 v2, fd vd is equal to the just nothing special here. This is just the definition, right? v1 of v d over 2, the first d over 2 variables, times fr of the second v over 2 variables. And this is drawn from our distribution x1, xd. So now I'm going to do the same thing that I did before over here. I'm going to say, OK, we'll first draw the first d over 2 variables, and then I'll draw the second d over 2 conditioned on the first d over 2. Right? It's sort of the natural thing to do. So this is equal to expectation, where we draw v1 through vd over 2 from marginal on the first d over 2 variables of fl. And now, like I said, we'll draw vd over 2 plus 1 to vd from the rest of the variables. So I guess d over 2 plus 1. Sorry, it's a little notationally heavy. Conditioned on v1 through vd over 2. Right? Either we view this as from the link of these or just from the conditional distribution. On x1 d over 2 is equal to, let's call this VL, to VL of FR. OK, clear enough? I just split things in half. So now I can look at this as the adjacency operator of some sort of graph, right, between the first half of the variables and the second half of the variables. OK, I'm going to erase this now because we've gotten to the point. So instead of the adjacency matrix, I have some higher order analog of the adjacency matrix between the first half and the second half of the variables. This is typically called the swap walk, or the partite swap walk in the literature. OK. Can I cheat and get like 10 more minutes? How long do I total?
Oh, okay, yeah.
Not after. OK, so let me draw this graph. All right, so I basically now have over here, I have the projection onto the first d over 2 variables. Let me just write this actually as x d over 2. On the right side, I have the projection onto the remaining variables, and I draw an edge right between v1, v d over 2, and v over d over 2 plus 1 to vd, when their union forms a full tuple in X, right? If and only if the tuple v1 through vd is in X. This is typically, OK, this should actually be a weighted graph. Right, what is the weight of this? It's just going to be the probability of vd1, of these variables conditioned on starting from v1 through vd over 2. It's exactly what you expect. I'm not going to write up the exact probability calculations.
Just the marginal distribution, right? Like you take the whole thing, you look at the marginal on just the first half of the coordinates.
Right, so these two sides are the marginal of the first half and the marginal of the second half, and I draw an edge when they actually connect to a full face in the hypergraph. Right.
So it's the marginal of like the function where you take an edge and then just project the two halves.
Oh, yes, yeah, right. This is also the graph, good point. This is also the graph that's generated by drawing a full tuple and then just taking the left-hand vertex to be the left half and the right-hand vertex to be the right half. That's another way to define this graph. Yeah, there's several ways to talk about this. So this is the swap walk. I guess this version of it was introduced in this paper of Dickstein and Denner. An unordered version was also independently introduced by Alev Geronimo Tolsiani. And we'll write this graph, or the adjacency operator, as s d over 2 to d over 2.
You're starting to get.
Oh, sorry. OK, so we'll write this as the swap walk between the first half and the second half. And let me just note that this can, of course, be made more general. Right? What have I done here? I've just taken two subsets of coordinates that don't intersect each other. Or generally, I could take any subset of coordinates of d, t1 and t2 that have trivial intersection. I could consider the analogous graph up here, right, between xt1 marginal and xt2 with the same definition. We have an edge when they form a face in the complex. And the theorem that we'll use, and that is in the exercises to prove, is that, so we'll call this version st1 to t2. It's this higher order analog of the adjacency matrix. That in a lambda product, this is in fact an expander. Right? So here is sort of the key lemma of the mixing result, that on a lambda product, I guess I should technically write the second singular value of s t1 to t2 is at most the square root of the size of t1, size of t2 times lambda of a lambda product. So this is proved via a very similar type of local to global argument that we saw in the last week. It's in the exercises. Maybe it's like a good exercise to do in the session today. It's a very simple argument. OK, so let me sketch the rest of the proof given this fact. It should roughly sort of just fall out. So we have, what, 4 minutes or something like this?
And the assumption for this is that it's a lambda product?
Yeah, sorry. This is with x, you can't see it. Yes. The assumption is that x is a lambda product. I wanted to get to, but I didn't. There's also the unordered analog of the swap walks. I can just draw it really quickly here, where we'll move between I sets and J sets by connecting them exactly when their union is an I plus J set. The disjoint, they're disjoint and their union is in the complex. And if we take this sort of partite cover of a two-sided object, exactly what you'll get is these partite swap walks. So by proving it, this is one of these examples, by proving it in the partite case, you automatically get expansion for this object or the theorem that you want in the two-sided case, which I think Siki will actually use in her talks, some version of this. Okay, let me very quickly sketch the rest of the proof of this. I mean, we're basically done, right? Now, I know I get to write this. This is exactly by definition. It's a little low, sorry. But this is by definition the expectation now of FL times the swap walk operator from the first half of the coordinates to the second half of the coordinates of FR. And now I can apply spectral expansion in exactly the same way that I did before, right? What I get, let me maybe move back to here. What I get is that the expectation of FL swap FR is at most expectation of FL, expectation of FR plus lambda times the 2 norm of FL times the 2 norm of FR. Remember, this is just the product of the first d over 2, and this is the product of the second d over 2. I'll be relatively quick here, but we're basically done. Why? Because we can use induction, right? The base case is just the graph case that we already had. These are now products over a d over 2 dimensional lambda product, right? So I already have, so I'll sketch it since we're low on time, but I already have that this expectation of FL is roughly the product where I equals 1 to d over 2 of the expectation of Fi plus some lambda error that I'm not going to worry about too much. Right, so this is just by the inductive hypothesis. We're in a lower dimension. We can apply it now. Similarly, we can bound this, right, by product I equals d over 2 plus 1 to d of the expectation of the Fi's plus lambda times some product of the norms. And since we're basically at the end of the talk, so here we can see that the main term we're done, right? We take these two products. We get the product from I equals 1 to d of the expectation of Fi, which is the main term that we wanted. And we're left with some sort of annoying set of error terms to analyze. Since we're basically out of time, I'll just claim that this is relatively uninteresting. All you have to do is sort of compare each of these values to the product of the d norms. Basically, just repeatedly using Cauchy-Schwarz, you can quite easily show that all of these products are bounded by this product of d norms. That's skipping, these ending error analysis details. That's the proof. You'll have to trust me that when you go through the recursion, d over 2 log d is exactly what you get from doing this type of recursion. Okay, I think I'm basically slightly over time, so I will stop. Thanks so much, everyone, for attention. Yeah?
Is the d log d loss necessary?
Yeah, good question. So that was a weak version. I do not know what the tight bound is. I know that you can get O of d times lambda. I don't know if this is tight. I don't know, Reed, do you know? I sort of suspect that I suspect the tight bound is d minus 1 times lambda. That's my suspicion. You can give a tighter bound by, what we actually did here was applied the expansion of the swap walks in each step. So you can give a version of the bound that's like, some coefficient that's based on the expansion of all of the swap walks, and you can be more careful with the analysis of the swap walks. You can be more, here I just told you that I applied Cauchy-Schwarz to bound these things, but you could be more careful. You could really go into this product and try to bound it again by a product of swap walks. That can save you the log d. But yeah, I don't know. I think it's open as far as I know.
I guess similar question. Is the tightness in that theorem over there, is that tight?
Good, yeah, so I planned to talk about this, so thank you for the question. This is essentially tight for small, yeah, thank you. This is essentially tight for small lambda. Let me show you the example. The example is in the unordered case. So let's say we have x is equal to n choose d. So just the complete hypergraph, all possible d subsets. What is this xi versus xj? Right, this is all possible. This ends up just being n choose I. Right, this is n choose j. And two sets are connected exactly when they're disjoint. Right, so I take an I set here and a disjoint j set here. So this is exactly the bipartite Kneser graph. And we understand the full spectrum of these graphs. And somebody should correct me if I'm wrong here, but I believe the second eigenvalue of the Kneser graph is known to be roughly square root ij over n. If you look at the complete complex, it's roughly a 1 over n local spectral expander. So you do get square root of size times lambda. So at least in the complete case, you actually match this bound. One thing I guess you could notice is that this bound is not non-trivial for all lambda. And we had this discussion of the down-up walks, that there was some version that was non-trivial for all lambda. That's also true. There's a bound of, I want to say, Lev and Parzanchevsky. Sorry for the spelling. That proves some sort of a Lev-Lau style version of this. It's something like 1 minus, I'm going to screw it up, but it's like maybe something like that. There is some version you can prove being more careful, but asymptotically as lambda goes to 0, it like the main term just becomes this. It should probably be square root of ij or something like that.
Are you saying the complete partite hypergraph is not a counterexample, but this?
Well, the complete partite hypergraph is just 0, right?
Okay.
The swap walk is it's fully independent.
The conversion between the partite and
Right.
bipartite
So
cases.
yeah. Okay. So I've cheated here. What I'm really doing is saying take this, take the partite cover of this, right, which is like all d tuples that don't repeat any value. If you look at the swap walk on that, it will just be a Kneser graph. And so the partite eigenvalue will be tight in that case.
It's really close to being a complete partite hypergraph, but it's not.
Yeah.
Yeah.
Yeah, it's very, very close. But so it's like a 1 over n product,
Okay.
basically. Yeah, good questions.
All right, I guess go to lunch. And the afternoon sessions start at 2.